Airline scheduling. The computational problems faced by the nation's largest airline carriers are almost too complex to even imagine. They have to produce schedules for thousands of routes each day that are efficient in terms of equipment usage, crew allocation, customer satisfaction, and a host of other factors, all in the face of unpredictable issues like weather and breakdowns. It's not surprising that they are among the largest consumers of high powered algorithmic techniques. Covering these computational problems in any realistic level of detail would take us much too far afield. Instead, we will discuss a toy problem that captures in a very clean way some of the resource allocation issues that arise in a context such as this. And as is common in this book, the toy problem will be much more useful for our purposes than the real problem, for the solution to the toy problem involves a very general technique that can be applied in a wide range of situations. The problem. Suppose you are in charge of managing a fleet of airplanes and you'd like to create a flight schedule for them. Here's a very simple model for this. Your market research has identified a set of M particular flight segments that would be very lucrative if you could serve them. Flight segment J is specified by four parameters: its original airport, its destination airport, its departure time, and its arrival time. Figure 7.17a shows a simple example consisting of 6 flight segments you'd like to serve with your planes over the course of a single day. 1. Boston, depart 6 a.m. To Washington, D.C., arrive 7 a.m. To Philadelphia, depart 7 a.m. To Pittsburgh, arrive 8 a.m. 3. Washington, D.C. departs 8 a.m. to Los Angeles, arrive 11 a.m. 4. Philadelphia depart 11 a.m. to San Francisco, arrive 2 p.m. 5. San Francisco depart 2:15 p.m. to Seattle, arrive 3:15 p.m. 6. Las Vegas depart 5 p.m. to Seattle, arrive 6 p.m. Note that each segment includes the times you want the flight to serve as well as the airports. It is possible to use a single plane for flight segment I and then later for a flight segment J, provided that A. The destination of I is the same as the origin of J, and there is enough time to perform maintenance on the plane in between, or B. You can add a flight segment in between that gets the plane from the destination of I to the origin of J with adequate time in between. For example, assume an hour for intermediate maintenance time. You could use a single plane for flights 1, 3, and 6 by having the plane sit in Washington, D.C. between flights 1 and 3, and then inserting the flight in between flights 3 and 6 to Las Vegas, arrive the flight Los Angeles depart 12 noon to Las Vegas, the problem. Arrive at 1 p.m. in a very general way as follows. Abstracting away from specific rules about formulating the problem, we can model this flight segments. We will simply say that flight J is reachable from flight I if it is possible to use the same plane for flight I and then later for flight J as well. So under our specific rules A and B above, we can easily determine for each pair ij whether flight J is reachable from flight I. Of course, one can easily imagine more complex rules for reachability. For example, the length of a maintenance time needed in A might depend on the airport. Or in B, we might require that the flight segment you insert be sufficiently profitable on its own. But the point is that we can handle any set of rules within our definition. The input to the problem will include not just the flight segments, but also a specification of the pairs ij for which a later flight j is reachable from an earlier flight I. These pairs can form an arbitrary directed acyclic graph. The goal in this problem is to determine whether it's possible to serve all m flights on your original list using at most k planes total. In order to do this, you need to find a way of efficiently reusing planes for multiple flights. For example, let's go back to the instance in figure 7.17 and assume we have k equals to 2 planes. If we use one of the planes for flights 1 and 3 and 6 as proposed above, we wouldn't be able to serve all flights to 4 and 5 with the other, since there wouldn't be enough maintenance time in San Francisco between flights 4 and 5. However, there is a way to serve all 6 flights using 2 planes via a different solution. One plane serves flights 1, 3, and 5, splicing in an legs SFO flights, while the other serves 2, 4, and 6, splicing in a pit, field, and San Francisco to Las Vegas. Designing the algorithm. We now discuss an efficient algorithm that can solve arbitrary instances of the airline scheduling problem based on network flow. We will see that flow techniques adapt very naturally to this problem. The solution is based on the following idea. Units of flow will correspond to airplanes. We will have an edge for each flight, and upper and lower capacity bounds of one on these edges to require that exactly one unit of flow crosses this edge. In other words, each flight must be served by one of the planes. If UIVJ, if UIVI is the edge representing flight I, and UJVJ is the edge representing flight J, and flight J is reachable from flight I, then we will have an edge from VI to VJ with a capacity 1. In this way, a unit of flow can traverse UI, VI, and then move directly to UJ, VJ. Such a construction of edges is shown in figure 7.17b. We extend this to a flow network by including a source and sink. We now give the full construction. In detail, the node set of the underlying graph G is defined as follows. For each flight I, the graph G will have the two nodes UI and VI. G will also have a distinct source node S and a sink node T. The edge set of G is defined as follows. For each I, there is an edge UI VI with a lower bound of 1 and a capacity of 1. Each flight on the list must be served. For each I and j so that flight j is reachable from flight I, there is an edge VI UJ with a lower bound of 0 and a capacity of 1. The same plane can perform flights I and j. For each I, there is an edge SUI with a lower bound of 0 and a capacity of 1. Any plane can begin the day with flight I. For each j, there is an edge VJT with a lower bound of 0 and a capacity of 1. Any plane can end the day with flight j. There is an edge ST with a lower bound 0 and a capacity k. If we have extra planes, we don't need to use them for any of the flights. Finally, the node S will have a demand of -k, and the node T will have a demand of k. All other nodes will have a demand of 0. Our algorithm is to construct the network G and search for a feasible circulation in it. We now prove the correctness of this algorithm. Analyzing the algorithm. 7.54. There is a way to perform all flights using at most k planes, if and only if there is a feasible circulation in the network G. Proof. First, Suppose there is a way to perform all flights using k prime less than equals to k planes. The set of flights performed by each individual plane defines a path P in the network G, and we send 1 unit of flow on each such path P. To satisfy the full demands at S and T, we send k prime units of flow on edge ST. The resulting circulation satisfies all demand, capacity, and the lower bound conditions. Conversely, consider a feasible circulation in the network G. By 7.52, we know that there is a feasible circulation with the integer flow values. Suppose that k prime units of flow are sent on edges other than ST. Since all other edges have a capacity bound of 1, and the circulation is integer valued, each such edge that carries flow has exactly 1 unit of flow on it. We now convert this to a schedule using the same kind of construction we saw in the proof of 7.42, where we converted a flow to a collection of paths. In fact, the situation is easier here since the graph has no cycles. Consider an edge SUI that carries 1 unit of flow. It follows by conservation that UIVI carries 1 unit of flow and that there is a unique edge out of VI that carries 1 unit of flow. If we continue in this way,
we can apply this construction to each edge of the form SUJ carrying 1 unit of flow. In this way, we produce k prime paths from S to T, each consisting of edges that carry 1 unit of flow. Now, for each path P we create in this way, we can assign a single plane to perform all the flights contained in this path. Extensions modeling other aspects of the problem. Airline scheduling consumes countless hours of CPU time in real life. We mentioned at the beginning, however, that our formulation here is really a toy problem. It ignores several obvious factors that would have to be taken into account in these applications. First of all, it ignores the fact that a given plane can only fly a certain number of hours before it needs to be temporarily taken out of service for more significant maintenance. Second, we are making up an optimal schedule for a single day, or at least for a single span of time. As though there were no yesterday or tomorrow. In fact, we also need the planes to be optimally no yesterday or tomorrow for the start of day n+1 at the end of day n. Third, all these planes need to be staffed by flight crews, and while crews are also reused across multiple flights, a whole different set of constraints operates here. Since human beings and airplanes experience fatigue at different rates. And these issues don't even begin to cover the fact that serving any particular flight segment is not a hard constraint. Rather, the real goal is to optimize revenue, and so we can pick and choose among many possible flights to include in our schedule, not to mention designing a good fare structure for passengers in order to achieve this goal. Ultimately, the message is probably this. Flow techniques are useful for solving problems of this type, and they are genuinely used in practice. Indeed, our solution above is a general approach to the efficient reuse of a limited set of resources in many settings. At the same time, running an airline efficiently in real life is a very difficult problem.